Today's speaker is Jonathan Park. Jonathan is a PhD candidate in HDFS working with Dr. Seaman Chow and Peter Molinar. Prior to beginning his PhD studies at Penn State, Jonathan earned a Bachelor of Arts in Psychology and a Master of Arts in Experimental Psychology with an emphasis in quantitative psychology from the California State University at Fullerton. There, his work focused on item response theory, test equating, and longitudinal SEM. In his work at Penn State, Jonathan studies discrete time dynamic network models, ramifications for non-directionality in these models, and methods for clustering individual processes to identify nomothetic trends in ideographic processes. Fun fact, that is one of his favorite phrases. Jonathan recently had his first paper pertaining to his PhD work published, and if you'd like to learn more about his work, photography, and how he made it to the front page of Reddit, you should check out his awesome website at jonathanpark.dev, which is where most of the information from his introduction is featured. So without further ado, please join me in welcoming Jonathan for his talk today.
Cool, thanks, Chelsea. That was a fantastic introduction. So today I'm talking about subgrouping with chain graphical VAR models. So I think I'll just get right to the point. I don't think there's much on this slide in terms of information. So kind of the overview of this talk, I'm going to introduce idiothetic methods as a concept. If you read the abstract, you know about it. If you haven't seen the abstract, then you'll get what we're considering idiothetic methods. And then I'm going to talk about the VAR as kind of the backbone for a lot of these idiothetic methods that we use, in particular, the ones that are going to be in this talk. And then I'm going to talk about the alternating least squares VAR as kind of the benchmark that we compare our algorithm to. And then the rest of the talk will be focused on the algorithm that we've developed, introducing the graphical VAR, the chain graphical VAR, or the multi-level graphical VAR, and then the subgrouping components that we developed. And then after that, we'll just go over a brief demonstration, like a simulated example and an empirical illustration. But before I kind of delve into what idiothetic methods are, I like to give context to this project. So 3 years ago, this tweet was posted by Sasha. I didn't know that you would come, but this tweet was posted 3 years ago. And 2 years ago, at my first QuantDev talk, I used this tweet to talk about the ramifications of modeling directionality. And that was kind of the purpose of my first talk, focusing on those first two sentences. But now, 2 years later, I can finally finish reading the rest of the tweet and read that last sentence, right? So gimme with graphical VAR would be cool. And in a sense, this project is not really gimme with graphical VAR, but kind of a spiritual allegory to gimme with graphical VAR. So I thought it would be appropriate to finally finish reading this tweet. And for those people that aren't familiar with gimme is a good example of kind of an idiothetic method. So I'm going to kind of introduce those. So for this talk, we'll define an idiothetic method as any class of methods that pools intra-individual information to derive nomothetic inference, right? So these can include things like the multi-level VAR, the multi-VAR by our own Zach Fisher, gimme, sgimme, and the ALS VAR, and a bunch of other methods. And the thing about these methods is that they are ways of looking at how individuals change over time, but also in identifying common ways in which multiple people change over time, right? So in ideographic process, kind of pooling those ideographic processes across people and identifying common ways in how people change over time. And these methods will differ in their allowances for more or less intra-individual variability, right? So something like the ALS VAR will fit the same VAR model to all of the subjects in a cluster. So they are assumed to have the exact same structure throughout the entire sample. But something like gimme will impose some group level structure, but also allow for individual variability in the network structure. And these idiothetic methods, really, a lot of them have seen a lot more use and development over the last decade, right? So there's Laura Bringman's multi-level VAR in 2013, the multi-VARs from 2020, gimme's 2012, sgimme's 2017, and so on. And I think a lot of this is associated with kind of finding that balance, right, between ideographic and nomothetic inference, where we know that n equals 1 will give us really good understanding of how an individual changes over time, but may not be generalizable, right? So if I'm looking at maybe an individual at risk of suicide, I can get a really good idea of their behavior over time, their network over time. But knowing how this individual is at risk of suicide doesn't really inform, or I can't really expect it to generalize to other individuals. And on the contrary, nomothetic inference, we already know from decades of research now that we can't expect kind of these average levels to generalize to any particular individual. So this idiothetic method is kind of, what if we got a bunch of individuals who are at risk for suicide, and then we try to identify commonalities in how they change over time. And then those would be our nomothetic inferences. And kind of apropos of that, the current challenge with a lot of these idiothetic methods is to identify or to deal with undiagnosed heterogeneity, right? So we can have samples of people comprised of distinct groups that have fundamentally different network structures. So I have two examples here, like distinct profiles. So we might have completely separate groups of individuals in our sample. So like MDD, major depressive disorder, versus typically developing controls. And if we just fit a single model to that whole sample, right, we can imagine we'd get a really biased network. Another example is if we had two subtypes of depression in our sample, which is more likely, right? We're pretty privy to whether we have depressed folks and controls, but we might not know that there are subtypes of depression in our sample. And in some cases, this could be really critical. There might be a specific pattern of connectivity for individuals who have major depression and are at risk of suicide compared to individuals that only have major depression. And so it'd be important that we'd be able to differentiate between those two groups before fitting some kind of idiothetic model. And so kind of with that, I guess I can talk about the VAR model, which again is kind of like the backbone for all of these analyses that I'm talking about today. Here we have a two-variate VAR1 model, which is just like one step back in time, where variables are at current time are predicted by the variables at the previous time step. So like an example could be like if I have loneliness yesterday, predicting my suicidal ideation today, right? So we can see how this would be useful in understanding how an individual develops over time. And if we could identify across enough people that this connection holds consistently, then that could be our nomothetic inference from these idiographic processes. But yeah, for the most part, the VAR is just looking at how variables at the current time are predicted by some backward step in time, by themselves, which are the autoregressions, and by each other, which are the cross regressions. And one brief thing I want to mention that will become relevant when we get to the graphical VAR stuff is that we have no contemporaneous effects, right? So in my example, we have loneliness yesterday predicting suicidal ideation today, which is a lag of 1 day. But it could be, and we really poorly understand kind of the time scale of suicidal processes. It could be that loneliness is more effective or affects suicidal ideation at a faster time scale than we can sample. So in the VAR, we can't readily estimate a contemporaneous effect. And so once we get to the graphical VAR, this will become relevant again. But I just wanted to mention that while I have this diagram up. So this is just the matrix notation of the standard VAR model. We have your scores predicted by basically the mean vector, regression matrix, and your scores at the previous time. But kind of relating back to this idea of contemporaneous effects, since we don't explicitly estimate those in the VAR model, that information of whether there are contemporaneous effects will get sucked up into this residual covariance matrix. And so again, I just want to point this out because it's going to become relevant when we get to the graphical VAR slides. But just know that if we don't model the contemporaneous information, if it does exist, it'll get sucked up into the residual covariance matrix. So kind of the standard VAR is introduced, right? It's just your variables at time predicted by some lag. And so we can get into kind of like the first clustering algorithm, which we compare ourselves to and against, which is the ALS VAR, or the alternating least squares VAR. And something that we can notice right away is that the ALS formula is a VAR model. It's exactly the same as a VAR model with some changes, right? So we've added subscript K, which is, instead of being a person-specific model, is a cluster-specific model, right? So we can have K clusters. So we have a cluster-specific mean vector and a cluster-specific regression coefficient matrix and residuals. And this other component that we added basically just turns on and off the equation for each person, right? So it's an I by K partition matrix where you're either a 1 or a 0. You're either in the cluster or not. If you're in the cluster, then the equation applies to you. If you're not, then it's all 0 and it doesn't matter. So really, this is kind of the basic idea of what the ALS VAR is we'll get K equations, and you're going to be in one of those, or your process will be described by one of those equations. And the way in which we know which cluster you belong to is by minimizing the sums of squares prediction error. I'm just going to call that prediction error from now on. But this is basically how we decide where you belong relative to however many clusters we get. We place you where your prediction error is minimized, right? And this is just iterating across all time and across all people. And I'm just going to do a really quick recap, right? So this is the ALS VAR. It has the PIK, which is the partition matrix. And again, it just turns on and off the equation. So whichever group you're in, you either get that equation or you don't. And then, like I was saying for this, is we know which group you belong into because the group that you're assigned to is the one where your prediction error is minimized. And then I had just gotten here. So again, this is quite daunting, but it's not that complicated. So we, at the very top, we fit a VAR model to each person, and then we just calculate the distances between each person using their regression coefficients matrix. And so basically we get an n by n adjacency matrix of how far people are from each other. And then we conduct hierarchical clustering using Ward's criterion. And that's kind of our like starting point, right? So we basically tell the algorithm, we feed it a given K value, right? So how many clusters do we want? And then Ward's criterion will partition the data set into that many clusters. And so for this example, I'm just going to say that there's 3 groups. So we'll just say, well, we're looking at 3 groups. And so we'll get from the clustering, that initial clustering at step 1C, 3 distinct groups of individuals. And then we'll fit a VAR model to each group, right? So each group will get one VAR model that describes them. And then what we do is we calculate those prediction errors for each individual to each group level VAR model. And then what we can do then is shuffle individuals into the clusters where their prediction error is minimized. So if Ward's criterion placed me in group 1, but my prediction error is actually lower relative to group 3, then we would shuffle me over to that group. And so we just do that dance with every single person. We just shuffle them around. And then we would re-estimate the group level VAR models. And then we just repeat that again and again, looking at whether we can minimize the prediction error by shuffling you to another place. And then once we can't do that anymore, once nobody needs to be moved, then we terminate the algorithm. And so then that would be the best solution for K equals 3, right? But then that comes with the limitation that we don't know what K is. We don't know what like an optimal value of K is. So then I need to, okay. So then it comes to the question of how do we decide which K is appropriate for the ALS? And the way that this works is by using the scree-test ratio plot. So what we're looking at is the number of clusters we enumerate, right? So we can have anywhere between 1 and n clusters theoretically. and then the sum of squares prediction errors. And essentially what we're looking for is the elbow in the scree plot, right? So I have this as an example here where we're at 2 clusters, and we're basically comparing the ratio of improvement from k-1 to k to k plus 1. And so we can see here that the ratio of improvement is, roughly 1. It changed by roughly the same amount. But then in this next slide, where we're closer actually at the elbow, we see that there's some non-zero degree of improvement from k-1 to k, but going from k to k plus 1 is some really, really small degree of improvement, right? So adding that extra cluster improved prediction error, but not by like any significant amount. So we can see here that our ratio is approaching infinity in this case, but then here it's close to 1. And so the way that we draw the decision as to which k is most appropriate is by selecting the value where the scree test ratio is maximized, right? Which would be this elbow. And we can kind of intuitively get that this is going to have the effect of, right, we're going to minimize our prediction error, but only to an extent, because we can just always keep improving and minimizing our prediction error until we get to like n equals 1. But it's not about minimizing prediction error for the cluster enumeration. It's kind of relative to cluster enumeration. So we want less groups, but we want to explain as much as possible. Right, so just like a brief recap for the ALS VAR, we get a k cluster solution. We basically set k max in this algorithm. You basically say, I think there's up to 10 clusters, and then it will check 1 through 10, look for that elbow, and then it will tell you how many groups there are and return the model fit. One, I guess, limitation is that it does force a common structure to everyone within that same cluster. So if you have really heterogeneous individuals, you can theoretically get a group where, yes, prediction error is minimized, but it's still not that great. And then the best model, right, the way that we select it is minimizing prediction error with respect to enumerating more classes, at least in the ALS case. And so Zach Fisher brought this to our attention when we were coding this, and it kicked our butts initially. We, when we were doing some simulation results or simulations against our algorithm, which is why we decided to include it, because it's a really good algorithm and it's really accurate. And so I guess now is a good stepping stone into the graphical VAR case. So I guess if the screen really did lag and you were just looking at the VAR diagram for like 5 minutes, then you have a good image of it in your head. But you can see here that the path diagram for a graphical VAR model is basically identical to the standard VAR, right? So we still have these lagged effects, right? So we still see, like, as an example, loneliness yesterday predicts loneliness today, but also loneliness yesterday predicts suicidal ideation today. So we still have these lagged effects, but the only thing that we're adding in addition to that is this thing called a PCC, a partial contemporaneous correlation. And that simply is looking at kind of the conditional association between variables within that time, right? So instead of looking at loneliness yesterday predicting my suicidal ideation today, this is seeing, is there an association after controlling for the other variables between loneliness today and suicidal ideation today? And we can see that the estimation of this contemporaneous effect is important, right? So sometimes we can't gather the data because of our sampling limitations or other kinds of things, but at least for the suicide literature, we know very little with respect to the actual time scale leading up to the actual act of attempting suicide. And so if we can extract this contemporaneous information, it's really valuable. And the graphical VAR lets us do that. Let's see. Yeah, so kind of touching on my points when I was introducing the VAR, the way that we get this contemporaneous information is by inverting the residual covariance matrix. We get this precision matrix called K. And just briefly, any off-diagonal elements of K that are 0 indicate that the variables are independent of each other after conditioning on all the other variables. But a non-zero element would be indicative of an association over and above the effect of all the other variables. And so from the graphical VAR, when we fit it, we get both the lagged network of what we would expect from a regular VAR model, but we also get this network of partial correlations in the contemporaneous space. And these two slides are really just like how we go from elements of K and convert them to the scale of the correlation, right? So ranging from -1 to 1 for the contemporaneous effects. And we also can do the same for the lagged effects. We can also scale them to the correlation scale from -1 to 1. And that's just, these are just those equations. I don't really need to spend too much time on this. So I guess this is kind of the group level aspect of the graphical VAR being the chain graphical VAR. The function in R is called multi-level graphical VAR. I just think it's really long to say that. And if we're willing to make some assumptions about our sample, then fitting a chain graphical VAR is fairly straightforward. So if we're willing to assume that a subject picked at random from our sample and that our sample is roughly homogeneous, we can make the assumption that our mean vector will be 0 and that there's some average phi and average K matrix, right? So some average matrix of lagged regressions and some average matrix describing the contemporaneous effects and noise. And so if we're willing to make this assumption, it's really straightforward to fit a chain graphical VAR model to our data. We just chain the time series, remove the first data point so that subjects don't predict each other, and we fit a graphical VAR model to the chain time series of our sample. And from that, we get kind of a network that describes the average lagged and contemporaneous effects of our sample. But like I said earlier, when I was introducing the idea of these idiothetic methods, if we have distinct subgroups in our sample, this can lead to a biased average network. And so that kind of is why we developed the subgrouping component that we have is for kind of parsing out that heterogeneity beforehand. So just to recap, graphical VAR model, if you're willing to make some assumptions, can be fit to the chain time series of multiple subjects. And those average networks that we get represent the average lagged and contemporaneous effects for your sample. And it does come with that cost, right? So we are assuming that there is some degree of homogeneity in our sample. But I guess I added this last point just as a contrast. So like things like scGVAR will give us output at the structural level. So we'll know that on average, people in this subgroup had this structure. An additional benefit to the multi-level graphical VAR, the chain graphical VAR, is that we get a parameterized group level network that describes the averages. So we actually get values in the structure, which can be useful to some folks. So then the question is, why do we cluster? So this is from actually like the first prototype I ever made of this subgrouping algorithm. I simulated 100 people. There's 50 people in one subgroup and 50 people in the other one. And we can see that the thing that differentiates the subgroups, right, is that there's this positive connection from variable 2 to variable 3 for the first subgroup. But for the second subgroup, there's this negative association between variables 2 and 3. And when we fit the chain graphical VAR to the whole sample, the average effect is nothing. And so if we have heterogeneity to this extent in our sample and we fit the chain graphical VAR, we might accidentally believe that there's no association on average in our sample, when in reality, we just have two distinct groups based off of structure. And I kind of want to relate this back again to this idea of suicide, right? So in the suicide literature, there are some key variables, things like depression, hopelessness, lack of connectivity with other folks, and impulsivity, and those kinds of things. And so if we have differences in the network structure for how those variables associate with each other, it'd be really useful if we could identify people who have a certain structure that may be more likely to attempt suicide compared to individuals who still have maybe a troubling connectivity map, but are less at risk. So if we could parse out that heterogeneity before we estimate these models, it'd be really useful for identifying kind of a common structure that exists for a lot of folks. I lost my mouse. I have no idea where it went. Found it. I can't click anything. Cool. So this is our approach to fitting a subgrouped chain graphical VAR model. You'll see some similarities between our approach and the AOS, right? So we begin by fitting n graphical VAR models. We fit one graphical VAR model for each and every person. And from that, we get our phi matrix, actually our PDCs, right? So our lagged effects. And then we also get our PCCs, our contemporaneous effects. So we have two matrices. And then we create an adjacency matrix where we simply count up the number of common paths between any pair of individuals, right? So for the ith and jth individual, we'll have a high number if we have a lot of common structure. And the way that we define common structure for the lagged effects, you have to have the same directionality and the same sign, right? So the same polarity. And then for the contemporaneous effects, you need to have the same structure as well as the same sign. And so people who are really common will have a really high number in this adjacency matrix. And people who are really dissimilar will have a low number. After we've gotten this adjacency matrix, right, we search it with walktrap and it returns cluster assignments. It tells us, you know, we think this is the best kind of cluster enumeration. And then from that graph, we calculate the average conductance for that whole graph. And we optimize conductance for all of A. So this is a little confusing, and the next couple of slides are dedicated to this. But basically, we check the conductance value across all values of A. So we subset this adjacency matrix by slowly shrinking values all down to 0 until we arrive at a solution where conductance is maximized. And so that's a little abstract. So then I promise the next couple of slides kind of address this. But the first question is, why do we optimize A? So the logic is that in this community detection stuff is that communities that are more similar should be densely connected to people in that same community. But then, and then we also expect fewer connections between me in community A with someone in community B. And as a kind of comparison, because this will be relevant, scGVAR starts by subtracting the minimum value from all cells. And this makes sense. So I have this example here of an adjacency matrix, right? And within these blue boxes are people of the same community. So we see here, this pair of individuals has 15 paths in common. Whatever the max is, I don't know, but they have 15 paths in common. But the same individual with someone in the other group, they only have 6 paths in common. So the scGVAR approach of subtracting the minimum, I guess in here would be 2. So subtracting 2 from all the cells would induce sparsity in the off-diagonal elements, and it would not reduce anything in the specific subgroup to subgroup connections to 0. But we still see that some paths would still be non-zero. So there's still a chance that we could accidentally move someone into a cluster that they don't belong into. And I don't remember what the slide is. Yeah, okay. So if we subtract out the minimum value, there's still a chance that we could misclassify a person. So then this slide is a comparison of the exact same adjacency matrices, but the one on the left uses the approach from scGVAR. We just subtracted the minimum value, whereas the one on the right uses this conductance optimization thing that we coded. And what we can see is that there were originally 4 groups. There's 13 people per group. And we can see that subject 4 here is misclassified in our example. And then in the minimum group, where we just take out the minimum value from the adjacency matrix, we actually merge 2 groups entirely. And so we have this one super group, and then we have 2 correctly identified subgroups. And this slide is also like a good place to talk about what conductance is. So what conductance does when you're trying to maximize conductance, what you're doing is you're trying to this is going to be a little weird. You're minimizing the number of connections going from one cluster to another. So visually, what we're trying to do is we're trying to minimize the number of red edges, right? So that's an edge that begins in one cluster and then goes to another one. We want to minimize that. So like this yellow group, for example, would have really high conductance because there's no edge leaving it and all the edges are self-contained. Whereas with the minimum value, we see that there's a whole mess of red everywhere. Let me go back here. So yeah, so after we've optimized conductance and we've identified our optimal subgroups, then we fit a chain graphical VAR to each subgroup. So to recap, right? So we'll fit a subgroup chain graphical VAR, and it allows us to identify in a data-driven way the heterogeneity that exists in our sample by optimizing conductance. And yeah, so the output that we'll get is much like Gimme. The way that I've organized the files is you'll get a group level network, so a chain time series to every single person, and then you'll get K subgroups, however many subgroups we find, and then you'll get the person-specific networks as output.
Jonathan, can I ask a clarification question?
Yes.
So you talk about basically, using the conductance as a way to find, right, a constant to subtract out of the adjacency matrix, so that you have you can induce sparsity, right? But you didn't talk much about use of lasso, right? So can you talk a little bit about that, and then mention what you found in terms of interactions between the two, or maybe you plan to talk about that later? If you can mention that, and also whether lasso is used in ALS, that would be great.
Yeah, so lasso is not used in the ALS. I actually cut out all the slides associated with lasso because I thought, yeah, either way. So the graphical VAR, as we use it, uses lasso regularization. And regularization is, let me find, do I have it anywhere? I'm just going to use this, right? So we're using regularization to penalize values in both the phi matrix and the K matrix to introduce sparsity into the networks, right? So I think really rarely you'll find a K, right, an inverted residual covariance matrix that doesn't have a non-zero element. So the regularization really helps to shrink down and introduce a bunch of zeros into those kinds of networks. And in a way serves as variable selection, right? So it only maintains kind of really strong coefficients, whereas weaker coefficients are drawn down to zero. I don't know, what was the other question that you asked, Seaman? I don't.
Just talking about how the two interact in some of the earlier simulations that you ran, because that is quite a critical point, because scGVAR, ALS, right? They don't allow for lasso, so they have this way of inducing sparsity, but it's a different kind of sparsity, right, than what you're inducing here. So yeah, it's worth emphasizing. Yeah,
that kind of reminds, I think this network, this image is really useful for talking about that, is that our adjacency matrix is comprised of counting up the number of common structures between pairs of individuals. And so there's two ways of introducing sparsity and two places we can introduce sparsity into that matrix. The first way is this way of optimizing the conductance and kind of manually removing the data. The other way that we can do it is through stronger regularization. So we can increase the strength of our regularization, shrink more paths to zero, and then by default, the A matrix that we calculate will be sparser to begin with. So there are really two ways for us to kind of introduce sparsity into the A matrix. I don't really, in terms of like the actual association between them, I know that we can get different results, but that's not really something, I guess, that I've, right, like obviously if we increase the strength of the regularization and we also optimize this adjacency matrix, we're going to get inevitably an even more sparse network of subject to subject connectivity. So I think that's something that people can play with, is that there's a lot of flexibility in terms of how much you want to restrict kind of the identification of the subgroups on either the model level or during this stage. But yeah, also, as Seaman notes, regularization isn't readily available. It's not available at all for the ALS right now. And then I think there is some kind of regularization in GIME, at least in early stages. But yeah, regularization is certainly included in the way that we estimate these subgroup chain VAR models.
Sounds great. Yeah, we can come back to this discussion later. I'm curious to hear Sasha and other people's thoughts, on this sort of sparsity related issues, but we can come back to that. So thank you, Jonathan.
Okay, yeah, no problem. So the rest of this kind of presentation is just focused on like these illustrations that I have, and they're not like fantastic. They're still running, so I'm sorry. But in this simulated example, we have 52 individuals divided into 4 subgroups. So there's 13 people in each group in a 10 node network. And I did this over 30 replications. The findings were basically exactly the same. So I'm only presenting 1 replication. We had 10 autoregressions and 9 cross regressions. And the way that those cross regressions were distributed was that there were 8 cross regressions that were specific to a subgroup. And then 1 was shared between groups 1 and 2, and 1 was shared between groups 3 and 4. And besides that, there was no overlap in any of the cross regressions. So the groups basically just shared 1 path at the subgroup level. And because kind of organizing PowerPoints is hard, I'm gonna spoil it right now that the true models are the graphical VAR models. And you'll see what I mean in a second. So hopefully it's not too confusing. So first off, we get this output from our function, which shows you the subgroup membership of all the individuals and who they're connected to. In this case, in all 30 replications, actually, we had 100% recovery of the correct subgroups for the graphical VAR. For the ALS, we actually merged 2 of the groups every single time, right? So instead of getting 4 groups for the ALS, we got 2 groups every single time for the ALS. So these are the results. So again, I want to say that the true network is the graphical VAR one. So like they're exactly the same. There's some bias, there's some downward bias because of the regularization, but the structure is the same. So the graphical VAR returned the correct subgroups and the correct structure. There's greater bias because of the regularization. And in contrast, the ALS merged groups 1 and 2 into this single subgroup. And the reason why we can kind of see that is that the common edge for groups 1 and 2 was this edge between variable 1 and variable 7. And we see that as being kind of one of the prominent edges in this subgroup. And in the next batch of individuals, again, this was a merged subgroup for the ALS, but we correctly enumerated groups 3 and 4, where the common path is between variables 4 and 9. And this kind of plays into how we expect kind of the ALS to work, right? So it's not about minimizing the prediction error in totality, but it's also about balancing the number of clusters that we enumerate. And so in this case, in these cases, it seems that it's good enough to enumerate the 2 groups. We're minimizing our prediction error by a lot, but we don't want to enumerate too many groups. Whereas with the graphical VAR, we are getting the correct number of groups in this example. And then I guess this last section is on our empirical illustration. These are just some characteristics of the sample. These data are taken from a paper by DeVos et al. In 2017. We had 47 folks. We had to remove 7 folks because of some estimation issues. But we had 24 people with major depressive disorder and 23 folks that were pair-matched controls. We had an average time of 83.2 assessments. The maximum possible was 90 assessments per person, and they were assessed on 14 affect items looking at positive and negative affect. So for the settings for our graphical VAR model, we set our gamma hyperparameter. So again, this is kind of going into the last regularization piece, but we turned that off. So instead of selecting models based off of EBIC, we're selecting them based off of BIC. And then we reduce the size of our grid to search 100 possible cells, as opposed to, I think the default is 2,500. And then for the ALS VAR, because we didn't know the number of groups that could exist in our data, we said just estimate as many groups as there are people. Or so it went from estimating one subgroup all the way over to 47. And the cluster solution that we selected was based off of that retest ratio that I talked about earlier. So one thing I want to note is that in the DeVos paper, they noted that their sample was incredibly heterogeneous, both within each respective group. So within major depressives and within controls, they found a large degree of network heterogeneity. And I can certainly confirm that we also found that in our results. And also the other thing is that we don't see a clean division between individuals who are depressed and individuals who were in the control group. So kind of going back to this, the first 24 subjects, so literally numbers 1 through 24 had major depressive disorder, and then the latter 23 were controls. And we see that the one kind of subgroup that came out is certainly not just 1 through 23 or 24 through 47. So we're not enumerating based off of like whether they're clinically depressed or not. We're just kind of identifying some common structures. And another thing I want to note is that the strongest amount of connectivity between any pair of subjects in that subgroup is, I think it was 70. There's 70 paths, which out of the total size of the network represents a little less than 20% of edges that were common in the network. So even though this is what our algorithm decides to be a fairly homogeneous subgroup, really the maximum amount of commonality was just 1 out of 5 possible paths that they had in common. So even this may be too liberal in identifying like a common subgroup. Nonetheless, this is the network structure of the subgroup that we found. And really, when I've looked at these data at the individual level, you really see either individuals that are strongly connected only in their, I guess like all of their positive affect items and all of their negative affect items are really strongly connected. And then you see other individuals where the connectivity is kind of randomly dispersed, or that there's a lot of connectivity going from positive affect items to negative affective items. And what we see here is the case of the very first example that I used, is that there's a lot of within affect connectivity, but there's not a whole lot of cross affect connectivity for these subgroups. There are some weak paths. There's this one particularly strong negative path between depression and happiness, but for the most part, is really just affective items map onto affective item, or positive affect items map onto positive affect items, and negative affect items do the same. And then we also ran these data with the ALS VAR, and interestingly enough, it came up with a 3 subgroup solution. I know that this is really hard to see, and I apologize, but I suck at LaTeX. And so what we can see are the 3 subgroups that were enumerated vary quite a lot in the actual structure, right? So the one on the left, it seems that on average, every single person has some, like cheerfulness is just getting beaten up in their network. It's very central, but everything is like affecting it. But either way, we see a lot of heterogeneity across the groups. But I would actually be interested in looking at the prediction error, which I haven't done yet. But yeah, so even though in our model, we saw a lot of heterogeneity, in the DeVos paper, they also note on the large degree of heterogeneity, the ALS seems to have found a 3-group solution, which notably does have distinct network features. And that's kind of like the final slide for this talk, is that idiothetic methods are a thing, and they're developing a lot. A lot of them have come up in the last just decade. The subgrouped chain graphical VAR model is hopefully a new way if we can finish this project soon. And Thanks to Sasha. Hopefully it'll be coming to the graphical VAR package soon. I do have a prototype of the tar file, so if you want a copy of it, you can email me. And yeah, so any feedback and inquiries can be sent to my email, and my website is there. Thank you so much.